All right, so let's continue to have some fun solving problems in Mathematica. What else would you want to do with a fine day like this? In our last video, we just did a very simple calculation. In this video, we're going to explore how to use Mathematica functions to do repetitive calculations. So we're going to start with a simple problem here, which involves computations associated with the ideal gas law. So here is the problem. We've got an ideal gas, and we're trying to calculate the pressure corresponding to 2 moles of gas when we have different temperature and volume conditions. Now, when we're using the same formula to solve a problem in Mathematica for different variables, the easiest thing to do is to define a function so we have fewer entries to make in our calculation. So we're going to define a function here which corresponds to the ideal gas law. Now in this case, that simple function, as you might recall from introductory chemistry, PV equals nRT. But since we're trying to compute pressure, we're going to just start with a simple P for pressure. Now in this case, the pressure is going to be a function of volume and temperature. We can also vary the number of moles, so I'm going to go ahead and add that, even though in this case we're going to keep the number of moles constant. So we're going to have 3 variables in our equation. So we do this by having a square bracket. We do this when we're defining a function in Mathematica. And with that square, after that square bracket, we go ahead and we list our variables. So the first one's going to be the number of moles n. And when we have a variable and we're defining the function, we follow that with the underscore. So we have n underscore, then we have a comma, and then our next variable is going to be volume. So we're going to do a v, and I'm going to use a lowercase v here so that we don't confuse this with other Mathematica functions. You have to be careful, as you recall, when defining variables and functions in Mathematica, that if we're choosing to use uppercase, that it doesn't conflict with something that's already embedded in the Mathematica program. So we have v, and we're going to use a small v here with an underscore, and then a comma. And for temperature, we're going to do T, and again, I'm going to use a small t here with an underscore. And then we close our brackets. Then the next thing we do, rather than just going for an equal sign, we're going to go ahead and do a colon equals, and this is a command sequence that delays the calculation because we're not calculating anything right now. We're just defining our function. We're going to calculate things in later steps, so we use the colon equals when we're wanting to do that. Okay. Now, so we have the colon equals. Now we enter our formula, and our formula is going to be n, all right, times r times t, little t, divided by v. Excuse me, should be lowercase v. And you'll notice that because we have nRT defined as our function parameters, that in the equations, when I type those characters, the characters have are italicized and also have a green tint in this case to it to indicate that these are indeed the same variables that I've entered as my function arguments. Okay, so I have defined my function. So now what I'm going to do is I'm going to hit Shift Enter so that Mathematica will evaluate it, and we'll then go ahead and enter our parameters. Now in this case we notice that we've got the ideal gas constant R, but we have not defined that. So what we need to do is, just as we did earlier in our calculations, we define it, and the best way to do this is to, again, freeform is, as I've said earlier, frequently the easiest way when dealing with units and constants. So we're going to go ahead and do it that way. Okay, so let's go ahead and do that. So I'm going to type in here in my next entry point. I'm going to do capital R, and I'm going to go ahead and do this because I know I don't have any conflict issues in Mathematica. with the uppercase. So do R equals, and then remember for free-form input, we're going to just enter control equals. All right, and then I'm just going to type ideal gas constant. And now, what are the units? You need to know a little bit here about the units you're going to use. There are actually several different sets of units you can use for the gas constant. I'm going to go ahead and use the atmospheres liters per Kelvin per mole. Okay, and then shift enter, and we wait as we do this. And of course, just as we indicated before, I could have also gone through the process of using the quantities function for Mathematica. So we do this by typing R equals, as we have done before. We seem to have lost my mouse. Okay, there we go. We do R equals, and we do unit convert and quantity, and then gas constant. Actually, the official name for Mathematica is molar gas constant, but we're just going to type gas constant because that will work. And then the units, liter, atmospheres, per Kelvin, per mole, close quotation marks, close bracket, and shift enter. And again, of course, we get the same thing. So again, it's typically a whole lot easier to do this by using the free-form method as opposed to typing in the unit convert, etc., and defining the gas constant. So we've got a gas constant. All right. So let's go ahead and do a pressure calculation for part 1 here. We've got 300 Kelvin, 1.5 liters. We can do this several ways. One is actually to define the variables beforehand, or we can just enter the numbers directly into the function. So we could go ahead, and I'm going to define it as variables, and because I'm going to show you something here that's important to understand in terms of how we define functions. So I'm going to say, the number of moles is equal to 2. All right, and again, we're doing units here, and so we're going to enter units along with our variables. So I'm just going to do a control equals to enter that, and just type 2 mole for that. And then what I'm going to do is, rather than going ahead and getting an output for each of these, I'm going to follow it with a semicolon, because you remember when we're defining things with a semicolon, we don't see an output, and I don't need to see an output here. And I'm going to hit return instead of the shift enter, because I'm just going to evaluate all of these constants, variables at the same time rather than individually. And so then I'm going to do my temperature is equal to 300, and again the same thing because we attach units to it. So it's 300 Kelvin, and semicolon, return again, and so my volume here in this particular case is going to be V is equal to 1.5, forget the control equals, 1.5 liters. Again, a semicolon to suppress output, and then shift enter. So now it's evaluating all three, and all three are input now into this. Now what we're going to do is we're going to go ahead and we're going to calculate the pressure. So I'm going to enter P corresponding to these three, and I'm just going to do N V T. That's the ordering. We go back up here to our definition. Make sure I've got them in the same order: moles, volume, temperature. And then I just hit shift enter. And let's see. reason that didn't work is because I hadn't reevaluated everything in this circumstance. So there we go. So we reevaluate it, and we get our pressure in atmospheres. So that's simple enough. All right, so let's go ahead and do then the second part of the problem. Now what I'm going to do here is I'm actually going to enter these values with different variable names, because what I want you to understand is that when you define a function and you define it with variables in that definition, as we have here, they're nothing more than placeholders. So I can actually, when I want to do a computation for the function, I can actually enter the numbers directly into the arguments for the function, or I can give them different names and just use those different names in the arguments of the function. So I'm not going to redefine the moles since they're the same, but I'm going to look at temperature, and this time I'm going to call the temperature Tp, okay, equal to 1,000 and I'm going to call it Vp equals 2 cubic meters. And shift enter. So now I've got that entered. All right, so now what I can do is I can go ahead and I'm going to do pressure again, but I'm going to enter TP, VP, volume comes first, then TP in that. And of course these names are different from those that were in the original function definition, but that's okay as long as we enter them within the arguments of the function in the proper order, and then shift enter, and I get a value here that is in liter atmospheres per cubic meter, which seems to not make sense, but let's go ahead and remember one of the things that Mathematica does when it does the computation is it uses the units as given. It doesn't necessarily do a unit conversion right away. If I want to simplify the units, the suggestion bar frequently comes up with that. So I'll get simplified units here, and so I get a number in pascals. Now what it did was it automatically simplified the units in terms of SI units, which are pascals. I can convert that to some other unit. For example, up here it was in atmospheres. Let's say I want my units to be in atmospheres, so I'm going to just type ATM here for atmospheres, and that will convert it over to atmospheres and give me the value in atmospheres under those conditions. Okay. Notice it's a whole lot smaller. Why is it a whole lot smaller? Well, the 2 cubic meter volume is significantly larger than 1.5 liters, so with the much larger volume, we're going to have a much smaller pressure. When we talk about the gas law later on, then you will find that we've got these relationships that you obviously probably learned in introductory chemistry anyway. So that is a brief introduction to how we use functions in Mathematica. In our next video, we'll look at how we can plot functions in Mathematica.